FA23 everyone. I am Shomo and this video is on Chapter 7, Numerical Integration. Okay, so Chapter 7 is all about how we can use numerical techniques to approximately solve definite integral problems. Okay, so what I mean by a definite integral problem is something like this. When we have a function, let's draw a sketch over here. When we have a function f of x, and we want to find the integral of f of x over the interval a comma b. Okay, so we essentially want to find this area, right? We want to find the definite integral of f over the interval a b. Yeah, but it's not always easy to find these intervals, right? And so when it's difficult to find this quantity, we can rely on numerical techniques. Okay, so we can rely on numerical techniques to approximately find these integral values. Okay, and the way the way we can do that is by using the Newton-Cotes formula. Okay, but before we get into the maths, let's just understand some of the visuals first. The idea of Newton-Cotes formula is that we have the original function here. Okay, we have the original function here, but what we want to do is we want to use some nodes over this interval a b. So this is node x0, node x1, node x2, node x3, just like how we did in polynomial interpolation. Okay, so we get some nodes, and these are equally spaced nodes. These are equally spaced nodes. Let's call them h. Let's call these gaps h. And using these nodes, we can obtain an interpolating polynomial, right? So if we have 4 nodes here, we will have 4 f of x values over here, and we can find an interpolation. We can find an interpolating polynomial here, which is p3 of x in this case, right? In this case, it's p3 of x. And now what we can do is we can find the integral of this p3 of x over the interval a b, and this will be the approximation of the exact integral. So if our approximation method is good enough, then it will be close to the exact integral. Okay, but again, it's a big if that our approximation method needs to be good enough. Okay, so that's the idea of Newton-Cotes formula. We find a polynomial using some nodes, and then we integrate that polynomial. That's it. Okay, so let's look at the maths. So we basically obtain a polynomial. We find a polynomial using the Lagrange basis in this case, and then we simply perform integration over the interval a comma b on this polynomial. Okay, and we end up with something like this. Okay, and this is gonna give us our approximate interval value. Okay, so let's look at an example, because that will be more concrete. Let's look at an example of the Newton-Cotes formula with n equals to 1. So this n equals to 1 implies that that a degree 1 polynomial is being integrated. Okay, so we perform integration on a degree 1 polynomial. Okay, now the idea is that we have some function here. We have some function here called the f of x, and we want to find the want to find the integral over AB. And what we're doing is, this is f of a, this is f of b, and what we're essentially doing is we're creating a polynomial. This polynomial is gonna be something like this, right? And if we integrate this polynomial over a comma b, over the interval a, b, then essentially we are finding this area under the curve. And that will be my approximation of the actual integral. So this is the polynomial approximation, and this is the actual integral approximation. Okay, so let's take a look at how this can work. So this is my p1 of x. This is I want to find a p1 of x. Okay, and p1 of x is basically L naught of x times f of x naught plus L1 of x times f of x1. Okay, so what's the value of x naught and x1? X naught equals to a and x1 equals to b. Okay, we want to find the integral over the interval a comma b. So x naught is going to be a, x1 is going to be b. Okay, and now what's going to happen when we integrate p1 of x? Okay, so let's do that. We want to integrate p1 of x over the interval ab. Right, this is what we want to find. And so essentially what I have in my hands is I need to solve this. p1 of x dx equals to f of x naught times this plus f of x1 times this quantity. Okay, let's move that there. Okay, now now since our polynomial is degree 1, I already know that I'm trying to find this term. Since my polynomial is degree 1, I already know that L naught of x looks like this: BA x minus x1 divided by x naught minus x1 dx. Okay, and if you remember, we took x naught to be equal to a and x1 to be equal to b. So let's substitute with these. Let's substitute that in: x minus b divided by a minus b dx. Okay, and we can keep simplifying this. We can take the coefficient out, 1 over a minus b times integral of ba x minus b dx. We're going to get something like this. Okay, and we can keep simplifying this. We end up with, so if you perform the integration, we're going to end up with this quantity, x squared divided by 2 minus bx. Right? Oops, sorry. Should be there we go. Okay, and if we solve this, or if we simplify this, we're going to end up with something that looks like this: 1 over a minus b times negative half a minus b whole square, which is equal to, which is essentially a minus b whole square divided by negative 2 times a minus b. Okay, so we can perform we can do the division here. They cancel each other out, and we're left with a minus b divided by negative 2, or we can also write this as b minus a divided by 2. Okay, we can write this as b minus a divided by 2. This is equal to the integration of L naught of x over the interval AB. Okay. Similarly, if we perform the integration of L1 of x over the interval AB, then we're also going to end up with b minus a divided by 2. Okay, so if we follow the steps of this math, we're going to end up with b minus a divided by 2 as well. Okay, so let's come back to the original p1 of x integration. We know that the integral of p1 of x is equal to f of x naught times ba L naught of x dx plus f of x1 times L1 of x dx, right? And let's just move this for now. Okay, and we've already found the results of these two. We already know what they are, right? What they are is f of x naught times b minus a divided by 2 plus f of x1 times b minus a divided by 2. Okay. Okay. Fine. And then we can just factorize this. We can just factorize this to get b minus a divided by 2 times f of x naught plus f of x1. Okay, and again we took x naught to be a and x1 to be b, so we finally end up with b minus a divided by 2 times f of a plus f of b. So this is the Newton-Cotes formula for degree 1 polynomials. Okay, again, yeah, so we simply first find the integration of this polynomial, which implies the integration of which is basically the integration of this this expression, and we eventually end up with this result. Okay, and just to be very clear, p1 of x dx equals to this. Okay, just to be very clear, this is what we're getting. Okay, so notice that there's a subscript here, I subscript 1. This is this means degree 1 polynomial is being integrated. Okay, and there's a famous name for this expression. This is called the trapezium rule. This is known as the trapezium rule. Okay, this formula is very important. This formula is very important. Okay, we're gonna take a look at how we can use this formula. Okay, so just like in this sketch, we essentially draw, or we essentially find the polynomial over the nodes a and b, and then we integrate that polynomial to find this blue shaded area underneath the polynomial line. This is P1 of x. Okay, fine. So this was Newton-Cotes with n equals to 1. What about Newton-Cotes with n equals to 2? We can also do that, right? As a matter of fact, we can do Newton-Cotes with n equals to anything. What does Newton-Cotes formula with n equals to 2 imply? What this implies is, let's take the same curve as before, something like this, okay? And we want to find the integral over a and b, right? We want to find the integral over a and b. So n equals to 2. This implies that a quadratic polynomial P2 of x is being integrated. So first we have to find a quadratic interpolating polynomial. Okay, and so for a quadratic polynomial we need 3 points. We need 3 nodes. These nodes are going to be x naught equals to a. These nodes are going to be x naught equals to a, x1 equals to a plus b divided by 2, and x2 equals to b. Okay, so we have x naught equals to a, we have x1 equals to a plus b divided by 2, and then we have x2 equals to b. Okay, that means we have these 3, f of a, we have these 3 values here, f of a plus b divided by 2, and we have f of b here. So using these 3 nodes, we can interpolate a polynomial, and this polynomial is going to look like, something like this, right? It's a very bad drawing, but essentially it's going to look something like this, right? And this is the area under the curve. And at the very least, visually we can see that this is a much better approximation of the integral than with just a straight line, right? Because with just a straight line, there's an error over here. There's a large error over here. Okay, so fine, that's all good. So essentially, what we're trying to do is we're trying to find the integral of P2 of x over a comma b, and this is essentially we're trying to find the integral of L naught of x times f of x naught plus L1 of x times f of x1 plus L2 of x times f of x2 dx. Okay, so I'm not going to go through each of these. If we perform the calculations, and again you have to replace x naught with a, x1 with a plus b divided by 2, and you have to replace x2 with b. What you're going to end up with, this nice little formula. I2 of f, which is equal to b minus a divided by 6 times f of a plus 4 f of a plus b by 2 plus f of b. And this here is called, this formula here is called Simpson's rule. We call this Simpson's rule. So instead of taking a straight line polynomial over the boundaries like this, we are taking, instead of taking a polynomial, a straight line polynomial like this, we are taking a quadratic polynomial that should give us a better approximation of the integral. Okay. So let's look at an example. Let's look at an example. Okay. So the example is we have a function f of x equals to e to the power of x. We have a equals to 0, b equals to 2, and we want to find two things. We want to find I1f and we want to find I2f. Okay, so I1f, and one more thing, just again, this I subscript 2 means Newton-Cotes with n equals to 2. Okay, and the previous one was, and this is correct, and this basically also means Newton-Cotes with n equals to 1. Okay, now we want to find I1 of f and I2 of f. So let's do that. Let's do I1 of f first. Just use the formula, which is, the formula is b minus a divided by 2 times f of a plus f of b. That's it. So that's 2 minus 0 divided by 2 times e to the power of 2 plus e to the power of 0. This is going to give you 8.389. Okay, 8.389. What about I2 of f? I2 of f, again, just use the formula. Yeah, so use the Simpson's rule formula, you're going to get this 2 minus 0 divided by 6 times e to the power of 2, so that's f of a, plus 4 times e to the power of 2 plus 0 divided by 2. Okay, plus e to the power of 0. And this is going to give you 6.4207. Okay, there's a vast difference. These two values are approximating the same thing, but they have they have a large delta between them. Okay, so what about the exact integral? If we're calculating the exact integral, of e to the power of x over b and a over the interval a comma b, where b is equal to 2 and a is equal to 0, right? So what we're finding is it's just ex 2, 0. That's basically e to the power of 2 minus e to the power of 0. And that's going to give you 6.389. So this here is the exact integral, right? This here is the exact integral. And as we can see, Simpson's rule is far closer to the exact integral than the trapezium rule, right? That's because, again, if we take a look at this graph, with Simpson's rule, we have a better approximation of the curve. But with the trapezium rule, we just have a straight line, and that's the best we can do. So naturally, the error is prone to be higher in this case. Okay, so the last thing I need to point out here is that so we can use Newton-Cotes formula for many different values of n1, 2, 3, so on and so forth. Okay, so but let's take an example. Let's say I want to find Newton-Cotes for n equals to 5. Okay, so that means that I have the initial interval. I have the interval AB, and I need so if my polynomial is going to be degree 5, then that means I need 6 nodes. Okay, so I have x0, x1, x2, x3, x4, x5. These are my 6 nodes. X0 is always going to be equal to a. x5 is going to be equal to b. Okay, this is in the context of closed Newton-Cotes. Okay, so closed, we're talking about closed Newton-Cotes formula. Inside closed Newton-Cotes formula, x naught has to be equal to a, and x5, basically the last node, has to be equal to b. And every other point, every other node inside AB should be equidistant. That means they should be equally spaced from each other. Okay, so that's x naught. Let's say this is x1, x2, x3, and then x4. All of these should be equally spaced. Okay, all of these should be equally spaced, and this gap, we will call it h. We can find this h. H is basically equal to b minus a divided by n. B minus a divided by the degree. Okay, and so the way we can find x1, x2, x3, all the nodes in between a and b is x1 is equal to a plus h, x2 is equal to a plus 2h, x3 is equal to a plus 3h, x4 is equal to a plus 4h, and also x5 is also equal to a plus 5h, right? So which is equal to a plus 5 times b minus a divided by 5. So that basically gives you x5 equals to b. Okay, so when we take x naught equals to a and x5, basically when the last node is at the end of the interval, this is in that case this is the closed Newton-Cotes formula.